Next, we're going to talk about the DBSCAN clustering algorithm. DBSCAN is one of the density or distribution-based clustering algorithms. If you look at the plot here, notice that the clusters are not filled in. For example, the clusters here have concentric hollow shapes, and sometimes their shapes are very different from the elliptical or the spherical shapes that are common with GMM or k-means algorithm. In that case, if we try to use a k-means algorithm, we find that the clusters are very poorly recovered. Clearly, there are two clusters here, but the k-means algorithm mistakenly puts the different cluster shapes in a spherical fashion. Also, it gives rise to several different clusters. If we use a DBSCAN on the other hand, it can correctly identify the three different clusters that are in concentric elliptical shapes and also horizontal shape. It can also identify outliers that do not belong to any cluster. In contrast, remember that all observations are put to one of the different clusters in a k-means algorithm or a GMM algorithm. The DBSCAN algorithm views clusters as areas of high density separated by areas of low density. Due to this rather generic view, the clusters found by this algorithm can be of any shape as opposed to a k-means or a GMM algorithm, assuming that the clusters are convex shaped. The central component to the DBSCAN is the concept of core samples, which are the samples that are in areas of high density. A cluster is therefore defined as a set of core samples, each close to each other, and a set of non-core samples that are close to a core sample. These non-core samples are not core samples themselves, but are close to a core sample. The data is partitioned into groups with similar characteristics or clusters, but it does not require specifying the number of those groups in advance. A cluster is defined as a maximum set of densely connected points. It discovers clusters of arbitrary shapes in spatial databases with noise. DBSCAN estimates the density around each data point by counting the number of points in a user-specified epsilon neighborhood and applies a user-specified minimum number of points thresholds to identify core, border, and noise points. In the second step, core points are joined into a cluster if they are density reachable. That is, there is a chain of core points where each of the core points falls inside the epsilon neighborhood of the next core point. Finally, border points are assigned to the clusters. The algorithm needs the parameters EPS, that is the radius of the epsilon neighborhood, and the min points, that is the density threshold. So the goal is to identify dense regions which can be measured by the number of objects close to a given point. So two important parameters are required, the EPS and the min PTS. The parameter EPS defines the radius of neighborhood around a point, and the parameter min points is the minimum number of neighbors within an EPS radius. Any point X in the dataset with a neighbor count greater than the threshold min PTS is marked as a core point. We say that X is a border point if the number of its neighbors is less than min PTS, but the X point belongs to the epsilon neighborhood of some core point Z. Finally, if a point is neither a core point nor a border point, then it is called a noise point or an outlier. The figure below shows some different points using min points equal to 6. Here, X is a core point because its neighbor is equal to 6. Y is a border point because the neighbors of Y is 1, 2, 3, 4, 5 which is less than mean points, but it belongs to the epsilon neighborhood of the core point X. The point Z does not belong to the epsilon neighborhood of a core point X, and its neighbors is also 2, which is less than the threshold 6. So Z is a noise point. Let us look at an example. We are going to look at the iris dataset, and we are going to use the dbScan function. Notice that we have to input the EPS and the mean points values. To check the cluster, we can choose the $cluster function. First of all, if we look at the variable that stores the dbScan approach, we see that there are several borders, seeds, and then total in each of the different clusters. If you want to check the cluster labels, we see that the different cluster labels have been in 0, 1, and 2. If you want to compare the cluster labels with the actual species, we see that dbScan does not perform very well, because if you notice that the virginica and the versicolor are not very well separated, so they all become one large dense area, which is why several of the versicolors and the virginica form the same cluster. Here is a small quiz. Here are the scatter plots of 3 different databases, and which of the 2 databases do you think is going to be advantageous for dbScan compared to, say, k-means? And the answer is database 2 and 3, because for the first case, the clusters are spherical in shape, and so k-means is going to perform very well. But for the second and third, the cluster shapes are very weird, and so k-means algorithm is going to fail. Finally, I have a few exercises for you guys to try, and I hope that you give them your best effort.